Well, hello guys, we're back. This is going to be a quick video today. Today we are going to be talking about getting control voltage out of our microcontroller. So in order to produce control voltage that's suitable for our modular synth, we need to convert, or we need a circuit that is capable of converting digital information into an analog signal, okay? This type of circuit is also known as an analog to digital converter, right? And there are many different types of circuits that can accomplish this. Finding the right one can be somewhat intimidating. Luckily for us, a lot of these circuits come pre-packaged as integrated circuits, and a lot of them use fairly common communication protocols. These are protocols like I2C or SPI. Some microcontrollers, like the Teensy or the Daisy Seed, already come with built-in digital to analog converters, but others don't. I happen to have a MCP4822, which is a 12-bit digital to analog converter. We're going to be making use of that particular digital to analog converter today, and we're going to be using a blue pill for this, okay? And the Arduino framework. All right, I also want to talk about another way of generating an analog signal from a microcontroller, and that is by utilizing pulse width modulation. And by passing it through a low pass, we can smooth that out and we can get a fairly smooth analog signal out of it. And lastly, since today we are talking about control signals, we're just going to look at a simple way of generating a sine wave signal in code and then run through our oscilloscope to look at this wave. All right, let's get started. Okay, so in order to understand what we need to do with our DAC, the first thing we need to do is look at the datasheet. In the datasheet, we want to look at the block diagram so we can get an understanding of what's happening under the hood for this device to see whether or not we need to add additional circuitry to further complement the signal. We need to look at the power requirements. We need to look at the layout considerations. We need to look at the serial interface for the device so that we know how to communicate with it. So let's take a quick look at the datasheet and see what this is about. Okay, so here is the datasheet. This is the block diagram. This package has 2 DACs. And one interesting thing that I see here is that the outputs are buffered. We can power this from a single power supply operation. It looks like we can go up to 5.5 volts. Power supply considerations talks about wanting 2 bypass capacitors. One is 0.1 microfarads and the other one is going to be 10 microfarads, and that needs to be a tantalum capacitor, right? So that's this C1 and C2 right here. And we want to put these within 4 millimeters of the pin. And then of course the serial interface section will talk about the SPI communication. Here's your typical connection. When we configure our microcontroller, we're going to figure out what pins from the microcontroller datasheet. We're going to get what pins are associated with SEK, MOSI, and CS. These are the pins that we're going to wire to this DAC. The power supply, we're going to get it from a regulator 5 volts, and we're going to use the 2 bypass capacitors on the power pin here. For the output, I'm going to just use the 4 volts for this today. So all we're going to do is just put a 1K resistor, and this would be fine to go directly into any other Eurorack module, because these things, as we saw in the circuit diagram, have op-amps, and so they can sync. And this will also provide a little bit of protection. So there's that much for the DAC. I'm going to come back to the code in a bit. Let's continue on talking about the hardware. The other type of DAC that we're going to be exploring today is the Hi-5 PWM DAC. One of the simplest methods to achieve an analog output from a microcontroller is by using a single PWM pin. This is not going to give us a smooth analog signal, but if we pass that through a low-pass filter, then we can smooth out that signal. However, while this approach is fairly straightforward, it won't give us the best results. To improve the quality of the output, we can combine two PWM pins, set different cutoff points for the filters, and then combine the two, which essentially sums the two signals together, and it allows us to create a much higher fidelity signal. By the way, this technique is also known as hi-fi mode. It is well documented, and you can find more information about this in the MOSI library. We're not going to be using that one today, by the way. We're going to borrow basically the relevant pieces from Matthias Levy's PWM version of Peaks. I've taken the circuit and just tweaked it just slightly, but it's pretty much the same. Now the code we're going to be rewriting, we're going to use the Arduino framework instead of the STM Cube. So let's take a look at the circuit real quick. This is the work that Matthias Levy did. I did not change any of this stuff. These values work great, as you will see once we get into the oscilloscope. So this first stage here is responsible for combining the two signals, pulse width signals, and removing the pulse width wave. And so by the time you get here, you already have an analog output, but it's then passed through another filter. And then from here, we're just conditioning the signal to get it up to a Eurorack level. So these values right here will increase the signal to about 4 or 5 volts peak to peak. I think it might be 4. I left this 33K resistor and this capacitor in here because this is an active filter, okay? And together with the 6.8. And this is here to also filter out some of that digital noise. I didn't want to have to recalculate the cutoff point of this active filter, so I just left it as is. So if you need to increase the signal in here, what I suggest is change the value of R1. The relationship between this and this resistor will help amplify the signal without having to change any cutoff frequencies for any of the filters. So this is why I changed this from a buffer to an inverting amplifier here. If you want a signal that is centered around the 0 volts, adding a positive voltage right at this point will shift the signal. The signal right here is in the positive side, but over here we invert it. So over here the signal is inverted and it's negative. So if you add a positive voltage, you're gonna bring it closer to 0 volts. So when you flip it again, it's gonna end up back in the positive here. So that's one way you could do it. Leave it up to you to see how it's best suited for your application, but these are the things that you can tweak. There's a lot of different DACs. The 4822 is just one of many. There's newer ones now that are cheaper. The 4822 is rather expensive and hard to come by. There are better DACs that are probably cheaper. You just have to go through the same exercise, right? You have to look at the data sheet and then you have to figure out how to use it from there. Not every DAC is going to use the same communication protocols, and not every DAC is going to be suited specifically for a certain type of application. For example, this type of DAC, while it's good for CV, it might not be good for audio. First of all, it's only 12 bits, right? So you're not going to get hi-fi audio out of this thing. If you are looking to use a DAC for audio, there are DACs that are specifically made for audio, and these types of DACs will use IA2S protocol. An example of this would be like the PT8211, which I actually happen to have as well. So maybe in the next video, we'll do one specifically for audio applications. So you need to consider what the communication protocols are. You need to consider what you're going to be using it for, right? Is it control voltage? Is it LFO? Is it audio, etc.? Then you also need to consider what resolution you can get away with. Here's a few things that we need to know when generating signals. The first thing is real-time calculation is going to be way more accurate, but will require a lot more CPU. And this is non-trivial. So the other way is to pre-calculate the values and then store them in some kind of value map. Now, this is going to be way more CPU friendly, but it's going to require more storage. So microcontrollers, we're not going to have a whole lot of storage. Choosing the right approach can be tricky. But lucky for us, there is a happy in between. There's a technique called interpolation, and this helps kind of strike a balance between performance and space. So with that, let's take a look at the code. The code is going to be available in my GitHub. Check the links in the description. I'm just going to briefly go through this and explain what's happening here. I created some classes here, an MCP422 object. I'm not using any libraries, as you can see, so that you can see how to write to this. Basically, to write to this, you're going to select which DAC you're using first, and then you're going to enable, and you do this by setting the CS pin to low. We're going to combine or create our message, which is going to be all the values that are needed for that particular sample in time. And then we're going to write to it, and then we're going to disable the pin by setting the CS pin back to high. And so when we send the data, we actually need to send this data 1 bit at a time. So that's what this bit right here is doing, is cycling through the data, and then it is either writing high or low. In this repo, there is an additional branch called SPI library. This is the same implementation of this 4822.cpp file, but it uses the SPI library, which results in fewer lines of code. I have also this simple wave generator here, which is using this cubic interpolation method. It's basically generating a table on startup, and then it's reading the generated files during runtime. There's another branch called Accurate by CPU Hungry. This one replaces the wave generator code. So instead of pre-allocating the values in a value map, it will do them real time. The PWM DAC, in order to get this to work, we need to change the frequency of the PWM to 125 kilohertz so that we can filter all of that out. We create a 14-bit value that then we split into two, an upper half and a lower half, and then we send it to each one of the two pins. And I wrote this in a way that makes it easy for us to code. So we can use the same methods to write the sample. So if you look at over here in the main.cpp, both objects, the PWM DAC and the DAC, they both have inits. Here's where I generate my wave at the start. Here there is some bits for configuring the sine wave that were created, a table of 248 values at a sample rate of 96K. This doesn't do anything. It's just as a starting frequency, right? This knob here can change the frequency. So when we're actually writing our samples, we're just going to see whether or not it's time to generate a new sample or get a new sample from DAC, right? And then we're gonna get it from that wave gen object, the wave generator, and then we're gonna use the sample and we're gonna write. Now, the wave generated sample is creating a 12-bit value. So I'm gonna send that value directly to the DAC, but the PWM DAC needs to be scaled because while this one is 12 bits, this one here is 14 bits. So the difference between 14 bits is a lot, just saying. Then that is pretty much it. Let's go ahead and see what's happening under the oscilloscope. Here we have the circuit laid out. Let me explain to you what's happening over here. So I'm using the Blue Pill microcontroller. This is a 5-volt regulator. I am using it to power the MCP4822, which is this chip right here. Here are my bypass capacitors, one tantalum, one ceramic. The 3 SPI channels, the 3 pins are connected. There are these 3 right here. And then output 1 is going to the yellow output, channel 1, which is creating that sine wave. Below here, these are 4 PWM channels. 2 are used for the top channel and 2 are for the lower channel. I'm not going to use the lower one today, so right now we're just using the top one. This is the same circuit that you guys saw in the slides. And I'm taking the output onto channel 2, which is the blue one. And so that's what that looks like. Let's change some frequencies and see if we can... You'll notice that as I increase the frequency, the graph starts to look a little bit more kind of pixelated. So let me clarify this a little bit. So when we increase the frequency over here, you see a lot more stepping. And there's a reason for this. Let's assume that this is a 1 hertz cycle. And the 12 bits, that's the resolution that interprets the values, say, vertically, right? Now the values sort of horizontally, those are, that's the sample rate. Okay, so that's different than the bit rate. Bit rate is the number of how many values you can have representing a particular sample. But sample rate is how many samples you can have over time. So say, for example, you have 44.1, which is CD quality, right? Now, CD quality is also 16 bits. So you have 16 bits of information. Over here, we have 12 bits, which is lower resolution. So what happens here is if you have one wave of 1 hertz, that's completing one complete cycle in 1 second. If your sample rate is 44.1, that means you have 44,100 samples for one iteration of that loop. But what if you have 10 kilohertz? Now you only have about 4 values. That's 4 samples, or a little bit over 4 samples that you can have to be able to identify that same wave, right? So if you can only define it with 4 samples, you're not going to get very much fidelity out of that. And so because of that, when you combine that with only a 12-bit resolution, it's going to hurt a lot, right? So this is why this is probably not good enough for audio, okay? But it's perfectly fine for control voltage because we're working at lower frequencies. Therefore, we have more samples that we can use to display or to hold the information about this particular wave. This is my understanding about it. If you guys have a better explanation for this, then leave some comments and enlighten us. Okay, so yeah, there we have it, guys. I hope this was informative. Hopefully this can help you in trying to come up with your own circuits and using this in some fun projects. Okay, so yeah, like I said, the code is going to be available for all the files, all the resource material is going to be available in GitHub. So check the video description for that. This was a hard one, and I have to say I'm still struggling with a few little things, but at least I now have a couple of tools that I can use for my future projects. So I think this was well worth it. DACs come in many different flavors. You need to know how to pick the right one for your application. We also learned that PWM is a form of DAC. It can yield great results, but it's going to require quite a few more components, and the circuits are going to be somewhat more complicated. A signal can be computed in real time or pre-computed by storing values in a value map. Each has their pros and cons, and there's even an in-between method. Great. Using libraries can simplify code. Okay, so with that, we have come to the end. Thank you for watching, making it through the end. I hope that this was useful, and do share what you come up with. All right, till next time, guys. Bye.